Chapter 5, Exercise 2. Alright, I'm going to go against my notes here and prove that it's a vector space first, even though the first thing I did is the whole inequality thing. So, let's prove it's a vector space. So, what we need to do is we first need to prove that it's linear. That meaning that if you add things together and multiply them by constants, that you can't leave the space. So let x, nope, let's not call it x. What did I call it? Let s and t be in L x, y. I'll just do it my way. And lambda be in, I believe the scalar field we're using here is C, or maybe it's K, where K can be R or C, whatever. Let's just call it lambda. Or let's just call the space, let's just say it's in C. It'd work the same in K. So let's see, we've got this. So since S and T are in L, X, Y, they have norms. So let the norm of S be CS, and, well, I guess it does technically make sense to first define that these three expressions are always equal, so that we have a well-defined norm here, but whatever, let's just stick with this. This part is easy enough that we shouldn't worry too much about it. Oh, we already have lambda in C. So then, what would be the norm of S plus lambda t? This is the infimum for all C, such that, see here, yeah, Sx plus lambda tx is less than or equal to Cx, and this is for all x. But now, I probably cannot fit this on that line, but so this is going to be less than or equal to, we just take this thing here and break this up in the natural way, so have Sx here, plus then the lambda comes out, then we get Tx less than or equal to Cx for all x. And then we can break this down further. Just looking at our definition here, and that's the main one we're using in this part, and we'll find out in the second part that this is all valid and stuff. So anyways, we put in these constants now. But then here, because we've got norm x's everywhere, we can just cancel them out, assuming that they're not 0, but if it's 0, then that doesn't really contribute anything, because if in the 0 case, the inequality will hold for all C. So anyways, we get this, but then the infimum over all such C that are greater than or equal to this, well, it's obviously just going to be this value, and this is a finite value. So hence, S plus lambda t is in L x, y. And so that confirms that. See here. To furthermore, let's see here. So now if we look at the properties of vector spaces, now that I think about it, this whole thing, the proving closure under linearity, that might follow from the basic properties I'm about to do, but I mean, I don't really care about the whole axiomatic, like, oh, how do we define things like in the first place and go from there. Like I know you have to be aware of that stuff, but here this is more kind of just elementary things that we have to check. So I'm not going to be too fussy about it. So anyways, what we're going to do is we're going to look at those actual those basic properties that you have of vector spaces. So properties of addition and scalar multiplication follow from the fact that they hold in C and thus see here. So let's see here, they hold from C and thus for functions mapping into C. So from here I mean the things like, you need things like commutativity of addition. So like you need, like, you take a function f plus g is equal to g plus f. But what you do here is you say, well, at every point f of x and g of x are complex values, and things are complex numbers are commutative, and thus these functions are commutative pointwise, and so the addition of these functions is commutative. You do the same thing for the properties of scalar multiplication. You do the same thing for associativity of addition, also distributivity, all those things. It all just works out very nicely, and I'm not going to go through all the details here. I'm just going to make, let's see here. So the additive identity is, let's see here, zero function the additive inverse of, say, f is minus f, which evaluates to negative, like at x, this thing evaluates to minus f of x. And the multiplicative identity is the number 1. Because you take the scalar 1 and multiply it by any function f, and you just get the function f at, it's a pointwise thing, and so it holds for the function. And so basically there you go. It's a vector space. Bunch of real elementary things, not anything that's like super important. This isn't like really esoteric stuff, so shouldn't worry you too much. And delete. Now let's prove that these three expressions are the same. Note that norm of x over the norm of x is defined and equals 1 if and only if x is non-zero. Thus, supremum over all, see here, tx, such that x equals 1 is equal to the supremum overall. Well, if you just divide this x through and bring it inside using linearity, this supremum, such that x is non-zero. But this is just equal to supremum of all tx such that norm x equals 1. See here. Next, for all x not equal to 0, tx divided by x is certainly going to be less than or equal to the infimum over all c such that tx is less than or equal to c x for all x. And that's just by the definition, because this is going to be the infimum over all of these c's. And so if you were to bring this x over to this side, then you have tx, you have exactly the thing on the inside here which holds. And taking the supremum on the left-hand side yields supremum over all tx over x such that x is not equal to 0. This supremum is going to be less than or equal to the infimum. We'll see. So tx is less than or equal to c for all x. See here. For the reverse, we have the infimum over all c such that tx is less than or equal to c x for all x. Well, this is equal to the infimum over all c such that tx over x is less than or equal to c. And x is not equal to 0. But let's think about this. The infimum over all c such that this happens certainly is going to be less than or equal to a particular c that satisfies this equation. And here's a particular value that will satisfy it. The supremum over all tx over x such that x is not equal to 0. This is a particular x, since this is the supremum, if you plug this in here, for every single x not equal to 0, tx over x will be less than or equal to the supremum, because this supremum is defined to be the supremum over all such things. And so we have this equality, and hence equality holds throughout. So there we go. This finishes the proof.